Hello, my name is Ashkbiz Danehkar. I am a research scientist at Uruka Scientifics. In this work, I present our principal component analysis of X-ray variability in the hard X-ray emitting symbiotic star. I did this study in collaboration with Jeremy Direct and Juana Luna. Symbiotic star consists of a hot accretion degenerator core and a cool giant star. There is a subclass of this symbiotic star which is called hard X-ray emitting symbiotic star, which produce hard X-ray axis above 3 kV. The origin of hard X-ray axis in this subclass is not well understood, but it could be an indicator of a massive white dwarf close to Chandrasekhar limits. There are a few hard X-ray emitting symbiotics. In this study, we consider RT-Crew, which previously found it has a soft thermal emissions at 1 kV, and also it has hard thermal emission of 10 kV. We consider the X-ray variability in these symbiotics, and we produce light curve in 3 energy bands, and using these energy bands we produce hardness ratio diagrams. In this hardness ratio diagram, which presented here, we see there is a transitions from the bright state to a fainter state in Suzaku data. And we use a modified version of Python codes for conducting principal component analysis, which is a technique for decomposing temporal variable data. And this package uses singular value decomposition function from NumPy package, and it's split a set of time slice energy bin spectra to principal components and eigenvalue and eigenvectors. By using eigenvalue, we see which component is statistically significant. Here the line show a correlations among logarithmic normalized eigenvalue with order higher than 3, which possibly produced by background noise. So the components which has departure from these lines could be statistically significant. Here you see XMMs, and the XMM data show some feature which could be related to thermal feature from soft emission as previously found in 2021. And here there is a component which produced by Suzaku data, and which could be associated with highly absorbed continuum. The first two components has 50% and 20% fraction contributions, which could be related to absorbing material and continuous. And the third order components, which has eigenvalue fraction of 9%, which has some feature similar to what we see with XMMs, and it could be related to self components with thermal emission of 1 kV, which previously found in Chandra data using Low-Kant's Bayesian statistical analysis. And here you see our study of Bayesian statistical analysis. And this soft thermal emissions has been seen in other symbiotic stars, which likely related to colliding winds. In summary, our hardness ratio analysis indicate that the source was harder in 2012 compared to 2007, and the principal component analysis of Suzaku data present 3 statistically significant components. The first is absorbing material with 50%, and then continuum with 20%, and then soft thermal emission with 9%. And also XMM data shows some features similar to C with third component of Suzaku data. In conclusion, there could be a faint thermal emission from soft component with temperature of 1 kV, which likely from colliding winds in symbiotic stars. and I would appreciate the NASA for supporting my research. And if you have any questions, you can contact me through my emails. Thank you for your attention.